Let's see. Well, we've just seen one application. Let's see another one. Which would be a corollary of the first application. Suppose we have suppose we have a CW spectrum with pi less than or equal n 0, then we the Hurwitz the Hurwitz map is an isomorphism. Here we already know what this is. We don't know the we don't know what the homology is. Well, the homology is defined using the same direct limit as the homotopy. Would you like me to write this limit again? I would say if you do, please let me know. Otherwise, we'll just go on. And the proof is we use what we've just seen. We may replace X with a spectrum without cells of dimension n or less. So by n plus 1 of X will be the limit by n plus 1 plus I x I, and this is isomorphic to the limit of h n plus 1 plus I x I by the usual Hurwitz theorem. And this is h n plus 1 of x. So for spectra, there's an analog of the Hurwitz theorem which works in exactly the same way as for spaces. And why sorry, x prime, x prime, x prime, x prime. Why do we have this? Well, because xi prime has no cells of dimension n plus 1 minus I prime. If otherwise x prime would have cells of dimension n or less. So we're able to apply the usual Horvath's theorem, and we do so. Well, to be on the safe side, we take I sufficiently large so as to get something positive here. Then xi will be simply connected, so we're allowed to use the Horvath's theorem, and we get this. So basically, again, for spaces, there's a problem. There's a problem with pi1. For spectra, there's no pi1, so we don't need to make any extra assumptions. Now let's just prove a few useful facts about spectra. So suppose we have a spectrum, not even necessarily an omega spectrum or CW spectrum, just a spectrum. Then okay, so I want to describe two functors from spectra to spectra, and to prove that those functors are isomorphic. Well, the first one will be the shift functor. I define the shift of x to be given by to have the same components, but with the shift. What does this mean? Well, this means, for example, that in component 0 we have the same space we used to have in degree 1. So we shift everything to the left. The next operation is suspending, which we just take to be the smash product with S1. And my claim is that those two functors are isomorphic in the homotypic category. Let's see. We already have a map from one to the other. So which of these we already know how to map into the other? Yes, so we have this map, which we have just by our definition of spectra. Now we need let's see that this map commutes with the structure maps. Well, it's I mean, the structure maps here are just the suspension of the structure maps for X, and the structure maps here are just the structure maps for X shifted by 1. So I have sigma xi sigma to which is S1 wedge xi wedge S1 to sigma xi plus 1, which is x I plus 1, which is 1. So we have this map from here to here, and the identity on the second component. Okay, so the on the other hand, we have a map from this space to xi plus 2 by the structure map, and here we have xi plus 1. So which is 1, and then I use the structure map on this factor. Let's see if the diagram commutes. Well, basically, unless I'm missing something related to the fact that we smash once on the left and once on the right, there's nothing really going on here. Okay, so now let's see. Let's see if this maps induces an isomorphism of the homotypic groups. No, let's we have two functors, and we have two functors, and we moreover, one of them, namely shift, is clearly an equivalence. I want to show that these two functors become isomorphic in the homotypic category. Well, to do this, and I have a natural transformation. To do this, I need to show that in the homotypic category, the natural transformation is an isomorphism. Well, this is exactly what this question asks. We have two functors. We have a transformation. Is this transformation an isomorphism in the homotypic category, which means does it induce an isomorphism of the homotypic groups? Well, let's see. By n of sigma n, sigma x is the limit of so sigma x I, by definition, we we take the suspension map by n plus I plus 1 so we suspend let me write just a double suspension here. Okay. So I want to write the recipe for calculating both homotypic groups, and then by looking at the result, I want to conclude that the result is exactly the same. Yes, but we want more than just homotypic groups being shifted in the same direction. We want an isomorphism, moreover, a natural isomorphism. Well, in this case, X will be just the wedge of the suspension spectra of its components. Well, this happens. Maybe with some shifts. So I want to decipher so here we have S1, which xi plus 1, which S1. Okay, and so here we have xi, which is 1. Okay, xi plus 1. Then I do the same thing. I do en plus I plus 1 sigma x I plus 1, where this time I take S1, which xi plus 1. X I plus 2. So here we have the suspension, here we have the structure map. And the horizontal arrows on the left and on the right are given by the structure maps. I want to know whether or not this diagram commutes. If it does commute, then this shows that the answer to the question is yes, because basically the homotopy groups are the direct limit of these maps on the one hand and of these maps on the other hand. Well, let's see. So this is given by the structure map, and so is this. Well, let me draw another arrow, which is basically again given by the structure map, but so I take the structure map on these two factors and the identity map of S1. Okay, so here my claim is that everything commutes. Well, we have this map, which is a structure map. And then we have this map, which is the same structure map, times the suspension. Wedge smash the identity of S1. no, x. So we need to we have this as the ith component. We need to suspend it. Sorry, there's yes, there's a mix-up with the indices. So here we have the ith component of. Okay, so here we if we put it like this, it would be correct. But if we want okay, I need the I plus first component of sigma x. No. I need the suspension of the ith component of sigma x. So it's just the double suspension, which means I have to take the. Okay. Yes. So sorry about the mix-up. We take this, and we need to suspend it. What do we get? We get the double suspension of xi, which is the same as 1 smash xi smash s1. And then we take the identity on of the left s1s, smash the structure map of xi smash x1 s1. So here, basically, what happens is we take this map and we suspend it, and we get this map. Since suspension is a natural transformation, we get a commutative diagram. Well, let's look at this square. Well, this square is basically the indices are all the same. So we only need to look at what happens on the level of spaces. Here we take the all maps are induced by maps of spaces. So here we use the suspension, the structure map on the second and the third factor, and then the structure map on this factor. And here we do it. So let's see. So this is x I plus 1 wedge plus 1. So here we do it the other way around. We first use the structure map on the first factors, and then the structure map on the last two factors, and well, the results are exactly the same. Okay, so the diagram commutes, and hence the okay, so so the limits are isomorphic. So the functors. So x goes to sigma x, and x goes to x shifted by 1. Are isomorphic in the homotopy category. What does this mean? Well, this functor is an equivalence. So this functor is also an equivalence. It's isomorphic to an equivalence, which makes it also an equivalence. In other words, in spectra, taking suspensions is invertible. And the inverse is the shift in the opposite direction. We already saw that the suspension is isomorphic in the homotopy category, of course, to the shift to the left. So the inverse would be the shift to the right. Well, there's another similar fact. Suppose we have a spectrum, which may or may not be an omega spectrum or a CW spectrum. Then we we define the omega of x to be the following spectrum. We just take the loop spaces of all components, and then we use the loop space approach to the structure maps. So I have a map from xn to omega xn plus 1 for all n. Very well. I can just take omega of this. And I get omega xn goes to omega omega xn plus 1. Very well. So this is the nth component of this spectrum, and this is the omega of the n plus first component of this spectrum. So I have maps from each component to the omega of the next component, and this gives me a spectrum. So I have this operation. Well, now I want to show that this operation in the homotypic category is isomorphic to the shift to the right. And if I do this, then I will be able to conclude that for spectra, as opposed to spaces, sigma and omega are just the inverses of one another. And or equivalently, each of them is isomorphic to the corresponding shift. Well, let's have a look. So, do I have a map in either direction? Do I have a map of spectra from omega x to x shifted by 1 to the right, or do I have a map the other way around? Well, yes. So we have these maps, and these are just the structure maps of the given spectrum. So we have okay, x shifted by 1. The nth component is just xn plus 1. sorry, xn minus 1, which goes to the omega xn. Very well. So this is x minus 1 n, and this is omega x n. Okay, so using the structure maps, I just get using just the structure maps, I get a map of spectra. Well, again, my claim is this map induces an isomorphism of the homotypic groups, and it's a natural transformation of the two functors. Well, let's check. Let's check the isomorphism part. So by n x by n plus I x n minus 1. So this is by definition the homotypic group, and for this spectrum we have the limit of again by n plus I omega x n. Well, for spaces we know that putting omega just replaces n plus I minus 1 xn, and well, oh yeah, sorry. Sorry, so xi minus 1 and I minus 1, yes, and here we have I minus 1. Yes, so omega x I. which is the same as this homotopy group of just x I minus 1. And okay, so we have the second formula, which is correct, and the first formula, well, the first formula is also correct. Well, let's see how the two compare. Oh, sorry. No, it's sorry. It's xi, not I minus 1. And then we just have two variables which we use to get to pass to the limit. So in fact, the two limits are exactly the same. But we need to compare. Actually, the groups which participate in the limits are the same, as opposed to this case where they were not the same. Where? Yes.
Yeah, so it shifts from the bigger group. from the group with the bigger number.
So
it must be it shifts from n plus I plus 1 to n plus I. So it must be phi n plus I plus 1 xi. And
oh yeah, yes. So yes. Thank you. Yeah, so if we replace I minus 1 by j, for example, here we have n plus j plus 1,
yes.
And we get the same result here. Thank you. Very well. Let's. Okay. So at least the groups which we have in both limits are exactly the same. Well, let's see what, well, let's see what this map does. Well, the maps, the vertical maps, are not do not necessarily induce an isomorphisms of the homotopy groups, except when the spectrum is an omega spectrum, in which case they do. So the individual groups are not mapped isomorphically, but let's see what happens. So in the first case, we just have the same sequence of groups as we had for X, but with a shift. Let's look at this one. At the second limit. So we have pi n plus I of omega xi. Then we need to take the suspension n plus I sigma plus 1 omega x I. And then we take the pi n plus 1 of okay, so so here I have a map from so this is a map which corresponds by junction to the map omega xi to omega x I plus 1. So we swap the omega on the, and this is the same as omega applied to the structure map of the spectrum. So if we swap sigma for omega, we get this. Now this is isomorphic to pi n plus I plus 1 of xi. Okay, and this is isomorphic to pi n plus I plus 2 of x I plus 1. And here we have okay, so we have the same map. So pi n plus I plus 2 of sigma xi. We suspend first, and then take the structure map. Okay, and my claim is again that this diagram commutes. Well, let's see. So we have isomorphisms. We have isomorphisms on the left and an isomorphism on the right. So does the diagram commute? And if it does commute, then why does it commute? Well, for spaces, no. This is definitely not a good thing to do. So, but for spectra, yes, these are well, as we suspect, these are the inverses of one another. But even for spaces, these functors are related, namely sigma is the left inverse, the left adjoint, and omega is the right adjoint. So what does this mean? This means well, we have a map from omega sigma to the identity to sigma omega. Okay, so we're sort of running late. Let's leave this as an exercise, and then one of the two. Actually, let's say it's an exercise, and then if I'll think about it, and if there are any non-trivial things involved in the proof, we'll sort it out later next week. Are there any questions? No? Okay, well then this is it for today.